Okay, super. I had the luxury of picking the time slot of the presentation for the Enerstock 2026, and I figured I'd challenge myself and take the one after the lunch break and try to get everybody motivated from the lunch nap and transition nicely into the rest of the talks. How can we use the so far untapped storage potential in our building stock by employing thermally activated building mass? I'm Christoph Rohringer, and I'm trying to answer that question today in a 15-minute crash course, let's say, of what we have done in task 43, which specifically dealt with that question. How can we use thermally activated building mass as a flexible energy storage technology? I'm saying we, and I mean the entire task 43 community. So we worked with many great scientists and people for the past 3 years to generate some answers to the questions, how we could work with TAPS as a flexible energy storage. And a great deal of the work I'm presenting today is done by others. From some, I have directly stolen some slides, so their names are on here as well. Shout out to them. To kick things off, maybe some definition. If you were to put thermal activated building mass or thermal building mass into Wikipedia, you get that definition. Basically, it tells you it's a technology that's not new, it's 30+ years old, and it's mainly used to regulate temperatures, so you can heat or cool buildings. As engineers reading that, we already see, okay, we have a potential energy storage at hand. Okay, we can overheat those components or we can subcool those components. We can use the heating circuits within these structural elements to store heat or cold. And this would allow us to use building masses as an energy storage of some sort within operational boundaries that are defined by the building occupants. I had this slide in the kickoff phase of the task some 3.5 years ago in 2021 or 4 years even. I checked it last week. It still says the same thing. So probably we as task 43 should edit the Wikipedia page. However, other things have changed in the past 5 years. Most people are probably going to ask ChatGPT first before they consult Wikipedia. I did that too. And surprisingly, ChatGPT mentions the thermal buffer. So it says using the building mass as a thermal buffer. So here the storage aspect is already in there. What is that storage aspect I'm talking about? We have seen a great deal of very interesting presentations, a lot of numbers and statistics yesterday and today already. And I figured what's the best way to convey the storage potential of thermally activated building mass. This is my take. This picture is the Käthe-Dorsch-Gasse. That's a residential and mixed-use city quarter in Vienna. It's about 30,000 square meters of conditioned areas. It's quite large, multiple buildings. And all buildings have thermally activated ceilings. We have monitored this city quarter for 2 years, and these ceilings are operated in a 2 Kelvin window. So they are modulated 2 Kelvin, I think between 20 and 22 degrees. And with that, a storage capacity is generated. And to put it maybe not into a number, but into a picture, we figured, okay, if we take the same amount of storage capacity that's within these buildings, within these structural elements that would have been built anyway, how large would a hot water buffer be? That it's comparable to this storage capacity. How large would that be? A hot water buffer storage up to 70 degrees, so much higher temperature spread, it would be that big. So that's maybe a good indicator of how much storage potential is actually hidden inside our buildings. That's a huge infrastructure. Somebody needs to pay for that. You need to build it, implement it, operate it. And we have this storage capacity available in the structural components that would be there anyway. So I think this is a good picture to illustrate the motivation for our task 43. How did we try to tackle the topic? Basically, we looked at the industry and the implementations, and we found that there's very little standardized use of TAPS as energy storage. There's a few lighthouse projects that deal with the topic, but there is no standardized way of doing it. And we were asking ourselves the question, why? And we found 4 core pillars that we think need to be addressed. So the first one is how you can build such storages in new construction. It's a little bit easier, but also in refurbishment. So Europe is built already, and there's a huge storage potential in the existing building stock. How can we operate those storages, those buildings, and integrate them also into systems? Then, and this is a very crucial question, you will see that later, how can we do business with such a flexible storage, and how can we also satisfy the customers and the residents? So we are talking here about the storage technology where people are living and working inside of. And the last one is, how can we increase reliability and trust in the technology by offering good KPIs that investors and implementers can really say, okay, we're going for that type of storage. First area of interest, so how can we build such storages? This is the classical way of doing it. So this is a picture from one of our industry partners. This is how you would do it in new construction. You have workers on site that put the pipes into the steel reinforced concretes and make the concrete slabs on site with some, let's say, a degree of error that is possible, and also that's a non-standardized workflow. However, you could think about the construction in a different way, right? So this partner of the task, Integration, it's a company from Germany, they are thinking in products. So they deliver tap elements that are prefabricated in a factory offsite with all the ducts and the piping already in there. And basically, it's a plug and play system that you just need to connect on the construction side. Here you can see how they do it. They even have a sandwich panel construction, so not the full concrete slab. It's very interesting to talk about gray energy and embodied carbon with concrete as a material. They use less and still deactivate the concrete that they do have. And here you can see how they prepare them in a very controlled environment in industry with all the ducts in there as well, and very little room for error. And this is how they arrive at the construction site, a product and not a process on site. It was really interesting to be in exchange with them. This is a solution, as you can see, that's more suitable for new construction. You can think about it in a refurbishment context, but we had a second industry partner in the task that really specializes on refurbishment, and that's Town 3000 from Austria. They have a product that's called ZIPA. That's prefabricated facade panels. So we go from horizontal to vertical, and that's slapped on the outside wall of an existing building. So you're using the existing wall material. Then there is a conditioning layer that heat or cools this existing building mass. On top of that, you have an insulation layer that guarantees that the overwhelming majority of the energy flux is going inside the building mass and subsequently inside the room and not to the ambient. This is a very interesting system for us because you can quickly implement taps and really use existing building masses without occupancy disturbance, and you have very fast refurbishment times. We did that now 2 times in a research project in Austria, but, and this is very important to me, there's already implementations on the free market, let's say. So not a research project, not a demo project, actual market actors buying that product from this supplier. So really a crucial point, there is market-ready solutions out there for taps in refurbishment. What they heavily advertise, and we also think is one of the main advantages of taps, is that you can, again, overheat or subcool these elements and store energy. And you can store significantly more energy with directly activated masses than with, let's say, if you were to use the radiators for indirect conditioning of the masses. To kind of underline that point, this is a graph from a colleague of mine, from Tobias Weiss, who calculated cool-down curves for buildings with convective heating systems and building with thermal activated building mass. So you can see here, if I get the pointer, the bold line is for classic building construction, the thin line for taps. And if you compare similar building typologies from the early 2000s, you can see that the taps building has a storage capacity like the factor of 3, let's say, that it cools down slower than the regular building. This is one of the key advantages of taps. However, it's also one of the challenges. As you can see, taps is also reacting quite slow. So in order to properly control it, we need to think a little bit differently than the standard solution for the past 50 years, where you just switch on the radiator valve and the room gets hot. We looked at this in the subtask B about the controller and ask ourselves the question, what's a good controller? How do you properly control it? And for some systems, you might even need a model to do it in a predictive way. And to show you the power of this, there's a slide from a partner, again from Austria, from a control research institute, who have in their own office taps equipped. And they looked at the performance of the taps after it was built and commissioned, and they found this. So this is a comfort band over the whole operation. And every point outside the comfort band is per se not comfortable. And you can see the operation was not very good. And then they changed the control, and this is on the right side in this picture. And for me, very important, they changed no hardware. They just changed the control regime. and they arrived at this super well performing operation from the aspect of comfort. And this is actually one of the trademarks of taps. If you properly control it, it offers very high indoor comfort. And this is just by adjusting the control. No valves, no anything, just adjusting the control. The indoor comfort is one aspect you can control the taps for. Another one is cost. So in the non-technical challenges, we also asked the question, what non-technical aspects are hindering taps deployment? And the first question is, how can I make money with it? Taps is, from the cost perspective, similarly expensive than floor heating. Then for a proper control, you need a little bit extra, let's say, and this little bit extra needs to be, there needs to be a reason for this, why you do it. So what's the actual benefit? One of the more easy or straightforward examples is if you were to use a flexible electricity tariff with a heat pump and a tap system. So here you can see Avatar, that's an Austrian flex tariff provider. It's just a random day from 2024. And already we can see if there is, let's say, storage capacity for about 4 hours, you can leverage 60% cheaper electricity price in one day. This variability in price increases the longer you can store the energy. And already this is an interesting prospect for a business case. Still, we asked the question in the task, also internationally, will Europe's rules, markets and policies allow taps to scale, to really scale? So not only some people using flex tariffs, but really to scale. And we came to 4 main conclusions, or let's say barriers that need to be addressed. The first is regulatory recognition. So at the moment, flexibility is not at the forefront of the attention, also in the EPBD. And we think it would be good to put the flexibility KPI in the EPBD. So people or implementers or real estate companies are actually building towards increased flexibility. The second point is, as you can imagine, a singular building does not offer meaningful load or storage capacity for an energy provider. They are thinking in different scales of power and storage capacity. So we need aggregators that pool together swarms of buildings to offer meaningful loads at a reliable pace as well. So we need to open the markets to aggregators for these sub 100 kilowatt assets. That's really crucial. Thirdly, the construction industry is a very slow one. We really need to train architects and facility managers, not only in predictive control, but also in taps in general, because they can only sell customers technologies that they know and that they're comfortable working with. So this is also a big point. And lastly, EU programs or in general funding subsidies should fund flex-ready buildings as easily as, let's say, heat pumps or PV roofs. It's really a crucial technology to alleviate stress from our grids. And it needs to be seen and funded as such. Speaking about funding subsidies, it's always tricky to come up with proper KPIs to also grade them. For this, we had our 4th subtask on standardization and KPIs. We tried to wrap our head around KPIs for flexibility. There's like 45 out there of them. You can find review papers. Our conclusion boiled down to this. Your tap energy storage system mainly consists of 3 things: the charging infrastructure, the taps itself, and the discharging infrastructure. I have 1 minute left, I see, perfect. The discharging infrastructure is mostly passive discharge. There's some systems with active discharge, but mostly it's passive. So we can, let's say, disregard that one. And that leaves you the charging infrastructure and the taps. And if you want to build a properly working taps, you really need to think about what you're going to want to do. I give you one example. If you invest in a very high power charging structure, you need to make, because you want to participate in the flexibility market, you need to make sure that your taps is big enough to allow the large charging infrastructure to operate for a meaningful amount of time. Otherwise, the business case will be mute. And this is my last content slide, let's say. I really want to bring that home. Designers and investors need to define the use case first, because before they think about taps. Do they want to bridge hours because they want to feed off of flex tariff? Do they want to bridge days, maybe weeks, or do they want to act on the flexibility market? And after having answered that question, they need to size each of the parts of that chain correctly to have a good business case. If you take home 3 things from this very dense presentation, the first point would be that there is materials and construction techniques for new, but also for existing buildings already on the market for taps as an energy storage. That the non-technical barriers are really the biggest obstacle for a widespread use. the technical stuff is figured out, but the non-technical is tricky. And that the proper control and system design requires a very clear intention and the cooperation of the crafts at the very beginning. Having talked about the beginning, I'm now at the end of my slides. So the task concluded end of 2025, and we expect the final report in summer 2026. And with that, I'm done, and thank you for your attention.
Thank you very much, Christoph. That was quite interesting, quite, as you said, quite dense. Yes, it was. But yeah, cool topic. I like it. However, we're going straight on to Hans-Paul Siderius, who is an energy efficiency expert at the Netherlands Enterprise Agency. And he's going to talk about, well, heat pumps for flexibility. And he was also took a look at Austria. Hans-Paul, please go ahead and enlighten us.
Thank you very much. Can you hear me?
Yes, very
And
well.
I think I did send you my presentation. Is that correct? Or shall I try to operate it?
I'd prefer if you operated it yourself because I don't have it on my computer right now.
Okay, I will
Probably be the easiest.
see whether I can.
I would
I
have
need-
it just in case.
Yes, please do so.
Yeah.
That's
Yeah.
because I now have to figure out. Well, here's the. Now, if you can do it, that would be
Yep.
convenient. Yeah, you're more. Thank you. More experienced in that. So good afternoon, everybody. My name is Hans-Paul Siderius. I work at Netherlands Enterprise Agency in the Netherlands, and I am a member, or we participate in the 4E energy efficient end use equipment, TCP, and the Netherlands also participates in the users TCP, and the project that I'm going to present is a collaboration of those two TCPs. From the 4E, the energy efficient end use TCP, we are interested in the products, the requirements on products, and the users TCP. They are, as the name indicates, interested in how users use the products. And we brought this together to make a very simple model for getting an idea of the flexibility potential for heat pumps. If you can go to the next slide. And flexibility here, we define that as the ability of a product to change power consumption as a result of an external signal. And we focus with heat pumps, we focused in this project on the contribution from households. So as in the foregoing presentation, there will need to be some aggregator to make that useful for the grid. But there are already, say, for instance, manufacturers or others that combine the input from a number of heat pumps to offer services on the market. And the aim of the project was to have a simple model to get a first estimate of this flexibility potential. And indeed, the emphasis should be on simple. And this presentation is about presenting the model and some results for Austria on heat pumps. We also in the report have some results on electric vehicles. And of course, the model we think could be extended to other products. Next slide, please. And first click. Yes, general setup is as here on the screen. There are flexibility resources. These are, say, products. So buildings could be, it's where you define the boundary. These can deliver a flexibility potential, so they can change their power consumption up or down based on or as a result of an external trigger. But there are constraints that that mediate so that not the theoretical resources potential is the flexibility potential that you get in the end. Next click, please. And this is the model in then a bit more detail. You recognize the flexibility resources, the constraints, and then the potential. The flexibility resources are the number of products. Of course, if you want to have the total flexibility potential for a country or a region, then you need to have the total number of products in stock. Of course, that can be differentiated, but here we looked at heat pumps. And you need to know the technical product flexibility. What is the average power that you can, as a maximum from the product, go up and down? These, as indicated, these resources are, there are constraints, and constraints in the upper line are first the number of capable products. At the moment, not all products and not all heat pumps are capable of receiving an external trigger. And then very important, and there the user comes into view. Not all capable products are enabled, although in most cases you need to do only the enabling ones. Still, this would require, at least in the setup that we have in Europe, enabling requires an action from the user. Then below there is the situational product flexibility. That is the power range that is available in a certain situation. So outside temperature, climate, location, season, building, that kind of parameters come into place here. And then you have, the next is the available product flexibility, because in all of these flexibility scenarios, mostly there is indeed the option that the user overrides the external trigger. Can be of all sorts of reasons, but that you also need to take into account. Then the number of products times the available product flexibility is the flexibility potential in watt, so the power, and the duration of the change, which of course will also depend in case of heat pumps on say the building characteristics and the storage that is available, gives you then the flexibility potential, the energy in energy terms. And going to the next slide, this is just for if you look at the slides later, because this is the small print which explains a bit more what I just said. And indeed, I read a question in the Q&A. Adding tanks for hot water can increase the flexibility potential because hot water tanks are a storage medium, and in general, flexibility is increased if you can decouple the demand from the user from the power input that you need to cover that demand. Next slide, please. Now we come first click. Now we come to what is the estimate for Austria. The number of heat pumps is around 850,000. The average product flexibility is around 1560 watt per heat pump. Next click. Then we have the first constraint of these 850,000 products. Most of them, almost 800,000, are capable, so we lose there about 6%. The technical product flexibility, and that was calculated at 0 degrees, is positive 800, around 870 watt, negative 700 watt. So that is from the average what you can go up and down. And then next click, and one more. There we come to the real constraints, because at the moment a lot of users are not willing to enable flexibility. These figures are not directly from a heat pump experiment, but they are derived from literature. There may be a conservative case, but whether it's 70%, 50%, it is clear that in this upper line, this is an issue that has to be tackled. And the lower next click, then also 1/3, also based on other data and literature, 1/3 of the users would override flexibility request because of all sorts of reasons. Could be comfort, could be, well, something else. So from this simple exercise, it was clear that apart from, of course, you need products that are capable, but then users are a very important part to get also this flexibility in practice. And next click, that's then the calculation that is just to give some insight in the numbers. And of course you can run, and we did that in the report, different scenarios where you get, if you have less conservative assumptions, a bit more favorable figures. Then the next slide, please. This is the model, but indicating the policy instruments that you could use to increase this flexibility potential. And as you can see, these are, of course, financial, technical. People need to be able to buy a heat pump. The heat pump need to be say capable and need to be connected to a network and aggregator, but also the behavioral aspects need close attention, because otherwise you have nice products in the home, but they will not be used. One of the questions is how much automation can help once people have ticked the box, I enable my product. If you have clever automation, they should not say directly feel the consequence of their heat pump delivering flexibility. As I said before, the trick for flexibility is to decouple the demand of the user in relation to the power, and apart from say behavioral aspects, also a good control system would help here. This was in short the presentation of the project. Next slide, please. If you want more information, there are the two websites of the 4E, the energy efficient end use equipment, TCP, and there the ETNA platform, and the users TCP. Also, you will find there the full report by which was done by the Austrian Institute of Technology on evaluating electric vehicle and heat pump flexibility potential, and also the contacts can provide more details, and especially Tara Esterl, who was leading the research, you can contact here. This was my presentation. Happy to answer any questions.
Yes, thank you very much. First of all, Hans-Paul. We'll have the questions answered in the Q&A session, which will be roughly from 14:15 on to 15. Therefore, we will now just step right on to the next speaker. That is Antón López Román. He's from the University of Seville, and he works in the energy engineering department there. And he was part of the, or he will tell us about the HYBRIDplus project, which we actually had in our newsletter in October, I think, a cascading PCM storage, which is quite interesting and quite useful for thermal and electrical coupling. So, Antón, please go
Thank
ahead.
you, Jan. Hello, everybody. Let me share my screen. Okay, can you see my screen?
Not yet.
Okay.
Is it me or is it? There it's coming. Yes, there it is.
Okay, hello, everyone. I'm talking today about the HYBRIDplus project and how it can grant flexibility through an electrified thermal energy storage system. So to put all of us on the same page, let's do a quick recapitulation of what a CSP plant is, a concentrated solar power plant is. It's this power plant that generates electricity using the sun as its heat source. It gathers the sun with mirrors into a focal point or a linear point and heat up a heat transfer fluid. This heat transfer fluid is normally solar salts in the state of the art of the CSP plants. These solar salts can reach temperatures up to 605 degrees, more or less, to be stored in quite a big direct tanks for the hours of storage to grant flexibility. And then this storage extracts the energy and feeds up a Rankine steam power cycle. These have a standard efficiency of around less than 40%, to say somehow. And we wanted to increase the efficiency of these power plants. So we intended to use supercritical CO2 power cycles to do that. But we have a problem there. Is these supercritical power cycles needs higher temperatures to reach good efficiencies, temperatures at about 600 degrees. This is not possible with the current technology. So we checked for a different thermal energy storage systems, and we proposed to use these phase change materials as an indirect storage system. These phase change materials are very have a very high energy density, so they are quite good in that regards, and they can reach temperatures much higher than this limit of the 565 degrees of the solar salts. But we also have to consider that the solar salts cannot be stored at that temperatures, but they can reach temperatures up to 610 degrees without degradation if it is for short periods of time. With this, we are able to use the same HTF, that is the state of the art, the normal one, to use our thermal energy storage system with low risk for degradation. This thermal energy storage system can be very easily hybridized to include electrical systems that allows for electrical charge. So we can use energy from renewables to charge our system. And we can also provide energy to the grid when it's required by the system, granting flexibility to the whole grid systems. Of course, if there's an excess of demand of energy in the grid, we just absorb the energy and store it as heat for later production. And this is the HYBRIDplus project that aims to demonstrate an electrified thermal energy storage system based on PCM in a cascade configuration for the next generation of hybrid CSP plants with supercritical CO2 power cycles. This is the base of our system, a cascade configuration with thermal energy storage. We divide it into a cascade system due to the wide range of the CSP operational temperatures that reach from 290 up to 600 degrees. So we are able to provide this energy in a very stable way. To do that, we gather 8 partners from different parts of Europe. We have 3 universities, the University of Seville, that is us, we are the coordinators and the developers of the thermal energy storage system. Then is the University of Lleida, that is a material expert that develop the materials that we need. The KTH Royal Institute, that's the techno-economic analysis, and there are 4 small and medium enterprise, Seiko, that does the electrification, B2Zero, that is an engineer company and also an end user, R2M, that helps us with destination and exploitation, Deutsches Metallfaserwerk, sorry there, we all call them stacks, it's easier for non-German speakers, and they are the metal wool developer. We are talking a little bit more on the metal wools later. And we have also one research center that have just joined us through the Hope on Call, that is Ottugunan, that are studying the electrification through induction. So how is our concept? How does it work? Well, we create this cascade due to the wide range of temperatures, as I said, and we get advantage of this latent heat of the PCM materials that allow us to store energy in a very, very high density way. By creating this cascade, we are able to get a much closer charge and discharge system, reducing the thermal hysteresis from the cycle. All the modules are the same, but have different PCMs. Each PCM have a different melting temperature that allow us to create the cascade. But the internal configuration is the same. All the modules are like a shell and tube heat exchanger with the HTF passing through the inside of the inner part of the pipes and the PCM stored in the shell. As you may know, the PCM has a big disadvantages. That is that it has a very low thermal heat transfer coefficient. To couple with that, we use these metal wools. These metal wools are just metal that is inside the PCM. We create like a composite to allow a very high thermal conductivity on the system that allow us to grant more power to our storage. It can charge and discharge much faster. In this configuration, we create the cascade with different numbers of modules per step to allow the granting the requirements of energy per step, since each PCM has different energy density. So this is the product or the solution of the HYBRIDplus system, and it's an electrified thermal energy storage, also called ETs. These ETs can be used both for electricity generation in CSP plants and for industrial process heat. So how do we grant flexibility? We grant flexibility through the renewable integration with our system that can absorb energy from excess energy in the grid, that is the typical sun hours, central sun hours, or when there's a lot of wind on the grid. We can extract the energy during these peak hours, convert it into stored heat, and then use it later for energy production or for the industry to produce. This can help decarbonize the grid and affects also the industrial heat that is very difficult to decarbonize. We can change in the industrial heat the use of fossil fuels for clean electricity from renewable sources. It's a very cost-efficient system because the energy storage can be stored as heat much cheaper than stored directly in batteries, and has a very low capacity and very long lifespans. We have a very wide range temperatures of operating temperatures from 150 degrees up to 600. So we can couple both electricity generation at high temperature or industrial heat at medium or low temperature. By using an indirect configuration, we are able to install our system with any kind of HTF that is already in the plant. This allows us to provide flexibility to the grid, even in installations that are already working. We can install this system in CSP plants that have not any thermal energy storage by design. That's quite typical in Spain. We have a lot of CSP that have not storage. We can retrofit them and grant them flexibility services. And it's also ideal for some industries such as the beverage, chemical, or textile, that we can substitute the fossil fuels generators to electricity generators with renewable energy sources and thermal energy storage. This supports the grid, helps peak shaving, and also can offer grid flexibility services, improving the stability of the grid. This is, of course, a very sustainable solution, and it's very aligned with the policies, with the latest policies, supporting climate goals, such as carbon neutrality, but also it's eligible for incentives, such as green financing in many regions. But why are we talking about the process heat? Because process heat is estimated to have a market of around $1.1 trillion by 2050. We have to remember that even though we grant flexibility to CSP plants and to grid generation, most of the energy right now is used as heat in the industry. An estimation is about 72% of the energy in the industry is supplied by heat. In this case, we have a wide range of energy demands from below 100 degrees and up to thousands of degrees, depending on the industry. And with our system, we can go from 150 up to 600. So there's a lot of margin there to work on granting flexibility through industry heat consumption. As our colleague talked before about heat pumps, we also consider that heat pumps are a very suitable solution for this, but they cannot reach all the temperature ranges. How do we do it? We just separate our cascade system and apply the cascade for each of the elements that we need. If an industry needs between 400 and 600 degrees, we just use 2 modules. If it's just between 200 and 400, we go to the medium steps with the correct PCMs for that industry. We can also go with a single PCM without any kind of steps that is, for example, very suitable for the steam generation that requires energy at constant temperature. That is really, really suitable for our solution that also provides energy at constant temperature. But this sounds really, really nice. We have a very big market, but we are not ready to it yet. The electrified thermal energy storage or the power to heat are not yet in a commercial, very strong solution. We need to break these development barriers to be sure that this product works. How do we do that? Well, we need to ensure a correct dynamic behavior, in particular during transients, ramps, startups, and shutdowns. We need to prove the different control strategies and to check if they are able to cope with the real demands. We need to guarantee a good homogeneity in the flow that is particularly critical if we are using HTFs such as molten salts, that we should avoid hot spots that can degrade the heat transfer fluid. And also in water steam generation, we need to check the multi-phase behavior to ensure that everything works properly. We need to consider the cycling effects, because in the end, we are working with several cycles per day with a thermal energy storage system. So we need to ensure that it has the ability to allow a lot of cycles during its operation. And also, it's imprescindible to check the degradation of both the equipment and the HTF used for transfer the heat to our product. All of this need to be validated, its performance at a relevant scale. And there is where the HYBRIDplus can help granting the flexibility, because we have prepared a platform for power-to-heat testing. So we can reach the full cycle of the power-to-heat cycle. That is, we have energy sources. We have an electric and inline heater that's around 145 kilowatts. We have electric embedded heaters, both in the thermal energy storage and in the HTF tanks. We have an energy sink with an air cooler of around 100 kilowatts. And we have 2 test modules for testing different kinds of thermal energy storage systems. Right now they are used PCM, but it can be changed and altered to prepare for the solution that needs to be tested. This both can work independent or in series operation. Also, the HTF tank that you use, right now we use solar salts, but it can also be used with ternary salts or the fluids. This power-to-heat demo platform is, of course, fully controllable. It's charged electrically with up to 200 kilowatts power availability for the power plant. It has a very high level of instrumentation and monitoring, and it can adapt to any kind of strategies and operation set points required to test any kind of thermal energy storage. This plant has been designed to be able to change the tests and to try different tests. And it also has blanketing available using nitrogen. It was really nice, the design, but we are already constructing it. This is some pictures from the actual construction. We expect to finish it in 1 month, more or less. So we will be happy to show it to all of you. And I would like to thank, of course, all the entities that allow us to do this work. There will be an union and the local government of Spain. Thank you very much.
Thank you, Antón. That was quite interesting again, and quite fitting to the next one. Our last speaker for today is Marco Prenzel. He will talk a bit about chemical parks and how to, well, basically use thermal energy storage in these, which is, I think, quite fitting to this storage we just saw. Marco Prenzel is a researcher and also project manager at the German Aerospace Center's Institute of Engineering Thermodynamics, and he's an expert in high-energy thermal energy storage, high-temperature thermal energy storage, I'm quite sorry. So, as you can see, he's already shared his screen, and I'd say, Marco, go ahead, please, and enlighten us.
Thank you very much for the introduction. It was indeed a very good first presentation because I can now start right into my topic. In fact, I brought some results from a previous project that we had at the DLR. This project is called TransDisChem, and in this project we teamed up with different companies from Germany and also the chemical industry to see how well we can introduce flexibility options into chemical sites such as thermal energy storage and power to heat. And in this manner, we can facilitate the integration of renewable energy and also reduce CO2 emissions. At first, I think it makes sense to understand what a chemical site is. Typically, it's a conglomerate of different companies and end-use processes. And these processes, they require energy, which in most cases is electricity and steam. And for this purpose, a chemical site typically has a central utility system. And this system consists of a combined heat and power plant. So it burns natural gas to produce electricity and steam. And if there's an undersupply in electricity, it's simply taken from the grid. Of course, we want to operate the utility system effectively, so it's constantly changing its operation depending on what the price signals on the market are. And our idea was to integrate power to heat and thermal energy storage into this utility system to see how the added flexibility can help in reducing CO2 emission and integrating renewable electricity from PV and wind. So I only have 50 minutes, so I have to focus on like one subject that we looked into during our project. And I brought the concept of a zero-emission chemical site, or how a zero-emission chemical site could look like, let's suppose, 10 years from now. You can see again the utility system on the right-hand side. Now a little bit more detail here. And I will just go through it one by one so that you understand what it's made of. So at the top, we have the energy supply side. We want to be zero emission. So it's based on green hydrogen and PV and wind power purchase agreements. These PPAs are pay as produced, which means that there's a direct, timely correlation between the electricity production and the use on the chemical side, which is like a true green energy supply. These PPAs can be curtailed, so they can be throttled, and the output can be reduced on purpose if it is required to do so. On the right-hand side, we have the energy demand. As I said, this is electricity and steam. A very large chemical site usually has a demand of a few terawatt hours per year. And in this case, it's about 1/3 electricity and 2/3 steam. And now we actually have the real utility system. There's some basics that you need, which is a gas turbine and heat recovery steam generator, gas boilers, and steam turbines. Almost every chemical site has those. And these are sized in a way that you could provide the entire energy for the end-use processes from burning green hydrogen. So you always have security of supply, even if there's no if there's no renewable electricity available from your PPAs. And then we have the flexibility options. This is either a power to heat, which directly converts electricity into steam, or we have a thermal energy storage, which can do the same thing, but it can also store the thermal energy for later use. So we heard about phase change materials in the previous presentation. I will focus on molten salt thermal energy storage. It's a well-known technology from concentrated solar power plants. You can see an example on the right-hand side on the bottom. This is the Undersol 3 concentrated solar power plant and the 2 large molten salt tanks. Now we are transferring this technology for use in chemical sites or under other industrial processes. A molten salt system is rather simple. It consists of 2 tanks. We have a cold tank around 270 degrees Celsius and a hot tank around 565 degrees Celsius. The molten salt is always in liquid form. So you charge the system by heating up the molten salt and storing it in the hot tank. Electric heaters are used for this purpose and surplus PPA electricity. And during discharge, the hot molten salt is used to generate high pressure steam. There's a few things to note here. First of all, the molten salt system fits quite well into the chemical side in terms of temperatures, because we have an upper storage temperature of 565 and the high pressure steam has a temperature of 530 degrees Celsius. So there we have a rather good fit. Another thing is during discharge, we also have steam turbines available in the chemical side anyway. So we can do a combined heat and power discharge, which is just an added bonus, so to speak. The storage tanks, they work like a buffer as well, which means that the charging side and the discharging side, they are perfectly separated from each other. So you could operate them individually. You can also operate them simultaneously and at different rates. So you can charge and discharge at the same time, and you're very flexible towards the PPA electricity and as it is produced. Well, another item that was mentioned in the previous presentation is that electric heaters are not TRL 9 yet. So there's still development going on. I understand that they are available on the market maybe at 5 or 10 megawatt, roughly in that size. But for chemical sites, we will need 100 megawatts or more. And there's still development going on. But the rest of the components, as you can see them here, they are state-of-the-art and proven technology. Okay, now we want to find out what's the optimal combination of PPAs, of thermal energy storage, of power to heat, and how do we operate them to reduce the cost as much as possible. And for that, we were using a software called Top Energy, which is a software for structural and operational optimization. Structural in that context means the sizing of the components. So what's the capacity of a storage system or the capacity of a PV installation, etc. In Top Energy, we built up a model of the zero emission chemical site. And then we're feeding it with input parameters. There's a lot of them. I will just go through the most important ones. Energy prices are important. So green hydrogen, the cost for the PV and wind PPAs, and also grid fees. And also the cost for the technologies is very important. So how much do we pay for a power to heat unit or the thermal energy storage system? And then Top Energy takes all this input data and the structure of the zero emission chemical site, and it produces the cost optimal design and operation of the chemical site. And as a result, we then get the energy mix, the annual cost, and what are the cost factors that contribute to this annual cost, and also the ideal component sizing. One thing to keep in mind, there are some components in the chemical site that are fixed, that cannot be changed in size. This is the gas turbine and the heat recovery steam generator, the steam boiler and the steam turbine. As I remember, these are sized in a way that it can supply the entire energy demand if required. And there's also components that can be optimized. This is the PV and wind PPA, or rather the installed capacity of the installation of PV and wind, the power to heat unit, and the molten salt thermal energy storage. And concerning the energy storage, the charging, the storage tanks, and the steam generator, so the discharging unit, they can be sized independently from each other. So on this slide, I want to show how the different flexibility options help to integrate renewable electricity into the chemical site. The diagram here shows the PPA electricity over a period of 2 days. So this is just 2 days in a representative year. And the fillings are in deep red, the integrated electricity, and in light red, the electricity that had to be curtailed. There's 2 more black lines in there. This is the electricity demand of the chemical site at every hour of the year, or of this 2 weeks, basically. And at the top, we have the total energy demand consisting of electricity and steam. So in the first diagram, we have no flexibility options. There's no power to heat. There's no thermal energy storage. And now what the optimizer tries to do is get the perfect mix of PV and wind PPAs so that we have a maximum possible integration into the chemical site. However, the maximum intake is limited by the electricity demand because we cannot convert electricity to steam. You can see that a lot of electricity is curtailed. So this is unused and needs to be paid for by a fee. And we still have a very big undersupply in energy. So the entire white surface that's below the total energy demand and everything that's curtailed, this needs to be covered by gas-fired components and green hydrogen, which costs quite a lot. So now we try to increase the intake of PPA electricity. And the first step would be to introduce a power to heat unit. You can see that the picture changes entirely. Now the new, let's say, limit to the electricity generation is the total energy demand, because we can convert electricity to steam, but there's still a lot of curtailment going on, and we still have time slots in these 2 weeks where we have an undersupply of energy. So still there is green hydrogen needed to supply the energy to the end-use processes. Then again, we can move to a thermal energy storage unit. There's still apparently a lot of electricity that there's an oversupply of. But now the thing with thermal energy storage is this oversupply we can now store using our 2 molten salt tanks and move it into those spaces where there's an undersupply in electricity, thus further mitigating the use of expensive green hydrogen. So now the question remains, how does this translate to costs, which is the most important thing? And here we have the final result of the study on the right-hand side. This is the annuity on the y-axis, so the annual cost. And we have our 3 different options, either no flexibility, a power to heat, or a thermal energy storage. The costs are made up of energy costs, so green hydrogen and the PPAs, curtailment fees, the demand rate, which is the use of the electricity grid to get the renewable energy. And of course, we have investment costs for power to heat or for thermal energy storage. Starting with no flexibility, as I said, there's only very little renewable electricity integration. and we need a lot of green hydrogen, which you can see here. Biggest block is green hydrogen. And the cost in general are very high as we need this green hydrogen, which is quite expensive. As we move to power to heat, electricity integration increases and we can reduce the amount of green hydrogen. There's a small amount of investment costs at the top, but for the power to heat, it's rather small, this contribution. And by just introducing a power to heat, we can reduce the annual cost by 21%. Now we move to thermal energy storage, and it perfectly aligns with the previous slide. We can further increase the intake of renewable electricity and reduce the green hydrogen demand even further. Now you can see that there's a rather high upfront investment that needs to be made to build the thermal energy storage system. And also you can see, for example, that the demand rate is rather big, which means that the amount of electricity that needs to be passed through the grid is rather high, and we need to pay fees for that. So to sum it up, benefits and trade-offs of thermal energy storage. It has the lowest total cost. You can see it's minus 21%, so even better than the power to heat. It maximizes the integration of renewable energy. In this case, it's 85% of the total energy demand. Don't let the diagram fool you. On the right-hand side, we have money, and this is total energy demand. It minimizes curtailment down to 6% of the produced PPA electricity, which also means that the land area for the PV and the wind installations, they are used very efficiently. There are some drawbacks, of course, from introducing thermal energy storage. First of all, we have a very high upfront capital investment, which is a risk. The space requirements on site, and also getting to emission-free just means higher energy costs. On the right-hand side in the diagram, I added a red line, which shows the energy cost from a different study that we did, where the energy came from the normal electricity and gas grid. Of course, we still have CO2 emissions, but the cost for the operation of the chemical site would be way lower. Zero emissions, it would be around 500 million, and with CO2 emissions, this would be around 300 million. So I'm seeing that I'm already running out of time a little bit, so I will skip over the conclusions and just come to the end of my presentation and say thank you. If there's any questions that cannot be answered during the Q&A, just shoot me an email. And I also linked my research here. Everything is open access, and you can read a little bit more of what kind of studies we did concerning chemical sites and flexibility. So thank you for now.
Thank you, Marco. Also, again, if you have a question, you don't even have to write Marco in person. You can, if it's bad, you can just write to us and we'll pass it on to him. So the question will reach him. All questions will reach everyone. And right now, we'll begin with the first question from the Q&A section. You can remember, you can always raise your hand and just ask a question. But the first question we have is for Christoph Rohringer, which is, it was there quite basically when you started talking. And it's quite an interesting one. It's by Geoffroy, and he's asking the picture with the large T-test tank in the middle of the residential area is quite striking and shows clearly one of the advantages of taps. But I wonder about the specific cost difference. Do you know how they compare? Because the T-test is much cheaper than individual small-scale household tanks of 100 to 200 liters. So yeah, that's quite interesting. How does that, like, how much more expensive is it to build a building with activated parts instead of just building a tank with water in it? How does that?
I picked it up. Hi, Geoffroy. Thanks for the question. Not that much, honestly. So we had this slide where we asked about the non-technical challenges, and we ran 50-ish interviews with practitioners and scientists in Europe. And we asked about the costs, like what's the additional cost of doing taps? And most of them said it's basically comparable to floor heating from the cost perspective. And we have the situation that in Vienna, for example, for all these newly built quarters, actually taps is in a lot of the tenders. And this is one main reason. With taps, you can cool as well. And that is very hard to do with floor heating. You could in theory, but there's some intricacies that make it difficult. So taps in the ceiling for heating and cooling is very well liked in the tenders. And I think the important part, maybe I used poor wording there. It's a hot water buffer, but that's storage for heating and cooling demand. So not individual tanks for hot water. They are probably separate in the rooms, but that should represent the storage capacity for heating and cooling. But the question is a good, let's say, ramp to underline the comment that the tabs in the implementation is not more expensive than floor heating. The thing that is complicated is get the control right. And this is where the delta is, where you need to find a justification why you would invest time and effort into a proper control of the system. I hope this answered the question.
It does to me. It did to me. Yeah, that's quite interesting. That especially that the control part is like the more complicated thing than the actually building it, which is quite simple. Good to know. Well, next question. Sorry. This one, I assume goes to Antón, because it's about CSP. If you know which is more efficient between solar PV and battery, so battery storage, and CSP and thermal storage. So how does that compare? Solar and battery versus CSP and thermal storage. Do you think the construction of CSP and thermal storage plants is going to increase in the near future in general? Will there be more of this?
Okay, let's see. For the first question, it depends on what you are going to do with what you store. I mean, if you are going to feed the electricity to the grid again, then of course it's much more efficient to use PV plus batteries. If we talk only about efficiency, because if you store it in thermal and then you need to convert it again to electricity, it's less efficient. But that is only for efficiency. When we talk about cost, probably here we have to define a limit of about 4 hours. This is more or less what the numbers we manage. If it's storing energy for less than 4 hours of operation, then it's cheaper with PV plus batteries. If it's more than 4 hours, it's cheaper with CSP plus thermal energy storage. In here, we also have to say a couple of things, that it's not all efficiency and cost. It's also what you can do with these storage systems. The CSP can provide services, ancillary services, and help the grid in ways that PV plus batteries cannot. There are different options for PV plus batteries that can also help the grid, but there are also other systems that helps more with CSP plus thermal energy storage. If we are talking about heat demand, then there's no much difference on storing as in efficiency. There's no much difference in storing PV plus batteries than using an electrical thermal energy storage. The efficient is more or less the same, but it's much cheaper to do it with thermal energy storage. Again, if we talk about the sustainability and the critical raw materials and so on, then the batteries also have some issues there that thermal energy storage does not. On the second question of if we are going to see more CSP plants, I hope we do, but it will depend on policies. From my point of view, it will depend on policies, because the CSP plants right now are not rewarded for all the services they can provide to the grid. So it's difficult to justify the cost of the CSP plant that is higher than a PV plant, of course. And they are not receiving all the revenues that they can provide to the grid. So making the answer short, if the policies do not change, I do not expect a big increase of CSP installations around the world. If the policies change and there are more share of renewables energy in the grid that needs the help of CSP plants and other technologies, then there is going to be an increase of installation of CSP plants.
All right, that's quite interesting, because that would have been basically my question about the whole cascading system, like how big the market for CSP currently actually is, and how it compares to the market for like industrial heat to use it for that. So how does that could you like give us just roughly like a percentage or something like how much would you expect your system to work in industrial settings compared to CSP settings?
I don't have a number now, but the advantage of our system is that we can use to retrofit actual CSP plants. And that's a very big point because around 50% of the CSP plants that are currently working in the world does not have thermal energy storage. So it's really easy to integrate this cascade system into those plants. But for that to work, they need to be able to charge the electricity they produce with this thermal energy storage. Up to this point, there are a lot of CSP plants that works on fixed revenues that have been signed when they started working. So if they install the CSP, the tests right now, the thermal energy storage, they are not going to receive any kind of benefit from that because they cannot sell that electricity. So that's why I go back to the policies. Depends on the policies if they are implemented to allow these flexibility services in CSP, then we will see an increase. But of course, the industry, the industrial sector for process heat, it's higher. It's much higher.
Yeah, I assumed it to be bigger because. All right, thank you for that. There's one more question for you, which I think I'll just do the last question for you because that is also one I find quite interesting. Could you give more details about the metal wool, manufacturers, materials, costs, and feasibility? Because I really enjoyed that aspect of your system with the metal wool and
Yes.
Anything special about it?
Yes, the metal wools are one of the big points of metal wools is that around 80%, 85%, 90% of it came from recycled material. So it's already a recycled material that are just cut down, recycled wire that are cut down to create just very, very thin wires. These wires are what we use to enhance the heat transfer coefficient of our PCM. We need to consider, and this is the difficulty of the project, but we already reached very good results, that these very small wires are compatible with the phase-change materials and do not degrade. And they work really, really nice. These metal wools are already being produced by our partner, Tax. Sorry with the name, I cannot say the real name. And they are producer of these metal wools. They adapted it a little bit for our solution, but they are producing it already, and they are being used for example, this is the kind of things you use to clean the lower part of your pan. They are very similar, and are also used for our industry to dissipate heat. So they are already a product being sold. We just adapted it a little bit for our solutions, but they really work really nice for the heat transfer enhancement. I don't know if I answered your question. Sorry, I just started talking and maybe I changed the topic.
All right, so that's it's basically just run-of-the-mill steel wool in that case.
Yeah.
That's quite interesting. All right, I think I'll go on with. Oh, there's 3 questions for Marco now. So I'll start with the first question for Marco, of course. First question by Jan Erhard is, during your talk, you mentioned that emission-free equals higher energy costs. In the context of thermal energy storage, benefits and trade-offs. From my perspective, this seems a bit misleading because the diagram indicates that thermal energy storage actually reduces reliance on expensive green hydrogen, which lowers overall system costs under the emission-free constraint. Did you also evaluate the annuity difference between a no flexibility scenario and a thermal energy storage enabled scenario based on current fossil energy sources?
All right, thank you for the question. Maybe let me first address the first comment. Yeah, maybe it was a little bit misleading, so I will try to make it more clear. So in the zero emission scenario, of course, thermal energy storage leads to the lowest energy cost and to the lowest overall cost. I just wanted to point out that going to zero emissions just means investing into technologies and also the need for bringing up more money for the energy. So there's just a an obstacle in terms of, or a monetary obstacle. So now coming to your question. In a fossil scenario, the use of thermal energy storage is in fact less pronounced because we also looked into this. The reason is if your energy system, for example, in Germany, relies a lot on fossil fuels, the price fluctuations on the electricity market are less pronounced because you still have a lot of power plants in operation, etc., and less renewable energies. And the thermal energy storage becomes really strong when there's a lot of price fluctuations on the market, because then you can take the low-cost electricity and use it for later times when the electricity costs are high. In this way, you have a lot of margin to reduce your cost for the operation of the chemical side. So for a fossil fuel scenario, in fact, just having a power to heat is already rather beneficial. And the added benefit of a thermal energy storage system is rather small in that case, at least around with the boundary conditions that we had. And in fact, one of my publications also considered this. So maybe you can look into one of those and just got more information on the subject of these scenarios.
That's always a nice thing to already have the answer in written form.
I'm glad that we had this study.
That's nice. All right. Second question for you. This is quite specific. In the energy modeling community, the problem you presented are standard, can be handled by open source tools like PyPSA, I guess, or OEMOF. I don't know these, but it's what they call. What was the specific reason for choosing Top Energy? Does it provide unique functionalities such as specialized industrial constraints or easier integration that justifies using a commercial tool over an open source alternative?
Okay, there's two answers to this. There's one very simple one. We had the developer of Top Energy in our project group. So they helped us in modeling the chemical side and were able to give us support. There's also another answer to this, though. Top Energy is a rather user-friendly tool. It has like a user interface with drag and drop components that are already available. And it might be easier to use for people who are not really well studied in energy system design. And so our idea was that we make a model of a public chemical site that everyone can use and take. And with Top Energy, they can get first hands-on experience with energy system design in the chemical industry. Furthermore, Top Energy is already used by a lot of different companies in the chemical industry that we know of. So the boundaries or the obstacles are not that big when you want to transfer your research into the industry and actually make use of it.
That seems, reasonable, especially the part with having the developer. That's very reasonable. And the last question for you, were there any ramp-up constraints of the technologies or any standby energy requirements?
All right, that's a very good question, which we also looked into. So in the final model that I used to do the structural optimization, there were no ramp-up constraints or anything included. The reason is we wanted to keep the optimization runs rather short. And with the model that I had, it was about 2 to 3 hours until we came to an optimal solution. Of course, you can argue, well, you're missing out information. Maybe it looks different if you have these constraints in your model. So to account for this, we did model validations beforehand. So what we actually did is we had Corenta in our project group, which is an operator of a chemical site, for example, in Leverkusen, Germany, or in Krefeld, Germany. And they have Top Energy in use, and they have very sophisticated models that include ramp-up times and shutdown times, standby energy requirements, etc. And then we used our simplified model, which is more fast and suited for optimizations, and compared it to their more sophisticated model and see how big are the differences. And in the end, the differences were pretty small. So we said, all right, let's keep the reduced model and just be quicker. And then we are able to investigate just more aspects of different constraints, different boundary conditions. And we are more free in doing the optimizations.
All right, that seems reasonable. So the final question we have in the question and answers is one for Christoph again. One Song asks, I would like to know a bit more about the control strategy. It seems to be optimization based. Are you using optimal control or model predictive control? I'm sorry. If so, what is the typical optimization horizon, for example, 24 hours or longer? And is there an open source repository available? Do we have that?
Yeah, perfect. Cool question. So I put some text in the Q&A, which is basically two emails, one of my colleague at AEE INTEC and one of the colleague from BEST. It is in fact model predictive control, what I showed in the slides, and this is also what we are working on. However, there was a lot of discussion, to not say backlash, with the industry partners, how complex the control really needs to be. And this was a lot of back and forth. If we really need the MPC, of course, we as scientists, we like to optimize every bit of percentage we can get out of there, and MPC is the most powerful tool for the job. I think we have 24 hours estimation for our own MPC, where we try to control as energy flexible as possible and as grid friendly as possible. There's no open source repository, but the two contacts that I sent in the answer to the question, you can contact them. They are working on projects, two different projects, two different types of MPC. And maybe one last word on the slide I showed with the results of the MPC. This, I think, is done with a model order reduction, because they needed to deploy the actual MPC model on PLC. And BEST, so this Austrian research institution, MPC is basically their core topic, and they always try to do a complex MPC to understand the problem and then do model order reduction so they can deploy on PLCs. That's the answer. So no open source repository, but open source colleagues. It's maybe equally good.
That's better than nothing. All right. Then I'll have one last question from my side. Oh, I see that Stefanie Tafelmeier wants to ask a question.
Yeah, sorry, I wanted to use the chance as there was everything answered, but sorry, Jan. So
Yeah,
maybe
please go
it's
ahead.
fast, but I wanted to take the last question maybe for Hans Paul regarding his model. I was curious because as far as I saw in your slides, you had to consider, you have to make assumptions regarding your flexibility resources, like the number of products, for example. And I was curious, how did you assess this number of products? And if there like plus minus a percentage of fluctuation, or how do you deal with the guess you have to make? Is there sensitivity analysis or something like this?
Thanks for the question. Yes, of course, you could do a sensitivity analysis. The numbers show were just, could say, a simple fill in, and the number of products were from several sources on the stock of heat pumps in Austria. And as indicated, of course, you could differentiate, because it might be useful to differentiate between heat pumps with a storage tank and without, or, well, that's, but that was not the intent of the project. The intent of the project was to show what a simple model can do on providing an estimate. And secondly, and there is also, I think, where the most say potential for improvement lies, the engagement with the users, because you can say, to keep the words, optimize on say the product level with a few percent here and there. If you then lose 70% because users think, well, it's not my business, then that is the thing you should go after first.
Okay, thank you.
Yeah, I just saw Christoph raised his hand as well, because I think that's quite an interesting aspect.
I have a follow-up question a follow-up question to Hans Paul regarding this aspect of how to increase the adoption of users, or how to increase at the end then the flexibility potential. So were you discussing some best practices within your study or within the TCPs and maybe in Austria, but maybe also in other countries. So is such kind of information out there on best practices to increase the flexibility potential?
There should be, although I don't know directly whether it's in the user's TCP or, for instance, I know that energy building and communities and also the heat pump TCPs, heat pump TCP are also looking into this. More, if you look more from, maybe you could say, a theoretical aspect, and that is always a big debate, how much. Personally, I think that you should automate as much as possible. So, of course, give the user overriding option, but keep the user out of this loop as much as possible and try to get as many people in. So the enabling and say that they just simply tick a box when they receive the heat pump, and make sure that through automation, the user is not aware of the heat pump or the EV or whatever household product delivers the flexibility. Because if you want too much interaction from the user, that is nice for the say the nerds, the 10% that really goes into every detail and controls things themselves. But yeah, you will lose the 90% others. But this is indeed, yeah, I think this is part of a debate, and also it's yeah, it frames a bit the solutions that you could look for. So yeah, this is a personal, could say a personal opinion, but I'm in basic, I'm a technician, technical engineer, so maybe there is some bias, I guess, in my opinion.